systems out of equilibrium. Please take it away.
Hello.
I would change the column.
Okay. Huh? What's I want to lower this so that you don't hear my breathing sounds. Can you still hear me? No. Very complicated.
Yeah. Now it's working. No. I can lower the volume.
Or I can try to talk more softly. All right. So, yeah, I have to apologize for a few reasons. The first is that I will never be able to do the type of board work that Guy just did. That was just incredible. So I have to apologize for that. My handwriting is going to be a lot worse, so you're going to have to get used to that. The other thing that I want to apologize about is that I'm tasked with teaching you about systems out of equilibrium, and this is a subject that's not in my expertise. So you lucked out, because we're both learning this together, and so maybe we'll both come out better for trying. Okay, so what is a system out of equilibrium? Well, I think the thing that most of you have experienced the most is the transition of a liquid. So imagine you have a cup, and you have a bunch of hydrogen atoms in here. They all have their own dipole moment. At high temperatures, this is a liquid. And then as you lower the temperature, the thing that you witness is that this forms ice. And ice is ordered. Right? You guys have seen ice before, right? Yes? Very good. All right. But what you might not notice, or what you might not know about water is that for it to turn into ice, you need to cool it slowly. So the fact that it forms an ordered lattice, this ice lattice, has to do with the fact that you take the temperature of the system to pass the critical temperature slowly. But if you go very quickly, then this freezes in a pattern that is completely disordered. And you have seen systems that look like this also. And this is what happens when you take fast cooling is how you approach something called a glass. So when I say a glass, I think most of you know what I'm talking about. For example, the cup that is the container of the liquid is itself a glass. So if you look at a cup microscopically, or a window pane, or any other of these types of solids, you'll notice that they're very different from the regular ordered pattern of ice or any other, for example, metal, in the sense that their physical structure is completely disordered. There's no pattern to it. There's no structure. But the physics of this transition is very important in a lot of systems. So, for example, if we didn't have glass, we wouldn't have, for example, optical fibers. This is what carries the internet. We wouldn't have egg freezing for people who want to have babies late in life. So this requires glass. So you might not have thought about this, but all of your cells are full of a liquid called the cytoplasm. And if you were to cool your cells slowly, then all of a sudden they would form ice, and you would get a rigid pattern, and it would destroy the cell. So you need to whenever you freeze, whenever you freeze any biological matter, you have to cool it super quickly so that it evades the ice transition. So you need to understand how to form a glass with biological cells. So, and the most important application of glass physics is ice cream. How many of you have taken a tub of ice cream, put it in your freezer, and all of a sudden when you pull it out of your freezer after having eaten it once, you notice that it's crunchy, right? That's the worst, right? And that's because actually ice cream is a glass. It's not ordered, and that's why when you make ice cream at home in an ice cream maker, there's this whole stirring process in order to avoid any regular pattern in the formation of the ice cream. So all of these things are glasses, and they're important in all aspects of life, but the transition from a liquid to a glass is a very poorly understood transition. We don't know how to define the transition itself. So what is, and I'll explain what is means, the glass transition. This is a very important open question in theoretical condensed matter physics. So we have many examples where we can form glasses, we kind of understand what we need to do in order to get a system to go from liquid to being glass, but as a theorist, we would like to have a theoretical definition of this transition, and I'll review how we define transitions in other systems so that you have a better idea of what I mean. But in general, the transition to a glass, we don't have a good definition for it. And you'll see a little bit as we go on through this course why that is. Are there any questions? All right, so let's start with a little survey of the audience. So how many of you think you understand the theory of phase transitions? Have you guys studied phase transitions before? Yeah, raise your hands. So I see some hand raised. Okay, so what's important in defining a phase transition? What do you think the important thing is? Some discontinuity, okay. Very good, that's the word I wanted to hear. So discontinuity is, it plays a role. It's not always there. For example, sometimes you have second order phase transitions that are continuous. But importantly, you have something called an order parameter. So we're going to review that for those of you here who don't know what that is, so just so that I get an idea. So Who here does not know this word, order parameter? Don't be shy, it's okay. Everybody knows the word order parameter? Okay, well, we're gonna review it anyway. Okay, so the purpose of this course is going to give you one example of a model of a glass and in which we'll understand and discuss a potential order parameter. And we're especially going to discuss the shortcomings of this description, of the order parameter. Okay? And so the model of the glass that I'm going to describe is not what we think of in the real world as a real glass. So all of these examples that I gave you, optical fiber, egg freezing, ice cream, these are what we call real world glasses. The model that we're going to study in this course is something called a spin glass. And there's a distinction between the two things. And hopefully by the last lecture, I'll get to discuss what the real difference is. Yeah.
Small question. The problem with defining a transition, is it the same problem as defining what the state of a glass is? Or is it two separate problems?
What do you have in mind when you mean the state of the glass?
I mean, how do you define glass phase?
Very good. We'll discuss that. That's the point. How do you define it? I mean, there's an intuitive understanding that the glass phase is a disordered phase. But the problem is that if you think of a liquid and you think of a glass, they're both disordered, but they're separated by a transition. And the whole purpose of studying the glass transition is to try and come up with a way of distinguishing the phases. So in the real world, the way that people discuss the glass transition is they define something very ad hoc. I'll come to it a bit later, but I'll give a spoiler now. So the thing that people do is they say, well, this is a liquid. This is also a liquid. But this is a liquid that moves very slowly. So what do I mean by slow? Well, I'm an impatient scientist. I have a time scale. Let's call that time scale 1,000 seconds. So I'm going to define a glass by whatever has flow or shear viscosity that's slow with respect to that time scale, 1,000 seconds. That's how experimentalists define it. But as a theorist, that's a horrible definition. We have to first input the observer, which is us, and then define it relative to the observer. So many people find that definition unappealing and incomplete. So, any other questions? Okay, so I'm going to talk about spin glasses. So I'm not going to talk about real-world glasses. And the reason that I'm going to talk about spin glasses is because they're just simpler. I can write down a model for a spin glass. But the important thing about spin glasses is that they do have a lot of the features of regular glasses. So I'm gonna get to that. So we're gonna build up very slowly. So I'm gonna first start with an example of a system that doesn't have a glass transition, but is built out of spins. And we're going to study that model completely. We're going to solve it today in the lecture. And then once we've solved the model, we're going to change it slightly so that it does have a spin glass transition. Okay, so that's the goal. But I want to say one more thing before I get into that, and it has to do with your question. So the way that I said that experimentalists define the transition from liquid to glass having to do with this observable, like the viscosity or the flow, well, that's a question of dynamics for the system, right? So how the system flows has to do with how it changes as a function of time. But when you study order parameters for other systems, like magnets, we can diagnose the transition using statics alone. We don't have to think about dynamics. And one nice thing about spin glasses is that those two things, the static picture and the dynamic picture, actually become linked. So I'll get to that, hopefully by either lecture 4 or 5. Okay? So everybody's okay with that? Okay. So let's start with a toy example. And this toy example is a system of spins, and it doesn't have a spin glass transition, but we're going to solve it. We're going to solve it in order to build all of the tools that we need when it comes to studying spin glasses. Okay? While I erase, feel free to ask questions. When did I start, by the way? $11:30. Okay. Okay, so we're not going to start with spin glass, but we're going to start with a model of spins. And this model that I'm going to discuss has a ferromagnetic transition. So this is a good model for a ferromagnet. And some of you may expect that I'm going to write down the Ising model, but we're not going to do the Ising model because it's one everybody does, so it would be boring if I did that one. Okay, so we're going to think of a lattice. And at each site, I'm going to put a spin, sigma I. So this is site I. This is site I plus 1. And at each site, I'm going to have such a spin. And my spins are not going to be plus or minus 1, but they're going to take values in minus infinity to infinity. Okay? So this is a model of n spins. I haven't specified at all how they interact with each other, but all I have, but I'm letting each spin take values from minus infinity to infinity. But of course, taking my spins to take these values, if I add a Hamiltonian that involves interactions between the spins, then if I take all my spins to be minus infinity, I could lower my energy very much, so the energy is unbounded. So I'm going to add a constraint. So my constraint is going to be that the sum over all the spins is equal to n. So what I'm basically saying is that the entire configuration of the system lives on a very high dimensional sphere. So each one of these spins, there's a non-trivial constraint that links the state of the entire system so that it lies on some high dimensional sphere. So the state vector is some vector pointing in n-dimensional space that lies on a sphere of size root n. Okay? And we're going to solve this model in mean field. So who knows what it means when I say mean field? I'm not going to let you answer. You average over the set of couplings. There's another way to there's another version of that. That is one definition of mean field. The one I'm going to use is that my interaction is not going to be local. All the spins are going to interact with all the other spins. So there's no notion of, I drew this lattice, but my Hamiltonian is not going to be nearest neighbor or anything like that. So I'm going to take my Hamiltonian to be this. I put the n here so that it will be nice later. So over all I and j, or over all I not equal to j. So there's no self-coupling. Sigma I, sigma j. So that's my Hamiltonian. What is this Hamiltonian saying? So I take any two spins, I lower the energy if the spins are pointing in the same direction, and I raise the energy if the spins are pointing opposite to each other. So this is a good model of a ferromagnet because you would expect that the lowest energy states are ones where all the spins want to align with each other, and then you will get a magnetic moment, an intrinsic magnetic moment in the system, at least at low temperatures. At high temperatures, there's thermal fluctuations, disorders the system. So at high temperatures, I don't expect the system to be in a ferromagnetic state, but at low enough temperatures, it should switch to a ferromagnet. So we're going to solve this model. Okay, so what do you think the order parameter of this model is? The expectation value of the spin. That's a good one, but then this depends on what site I pick. So let's do the average. I'm going to define this to be the average over all the sites, sum over I. So we'll say that this system is in a ferromagnetic state when this quantity m, the average expectation value over the entire system of the spins is not equal to 0. So this is the order parameter, the magnetization. So we're going to want to find a way to compute this expectation value. Okay, so let's start by computing the partition function of the system. We're going to compute the partition function of the system in the presence of a background magnetic field. And I want to remind you of a nice identity, the delta function I can write as follows. Okay? So my partition function will be the integral over all the spins e to the minus beta h I'm going to put the magnetic field. And then I'm going to do the following. I'm going to insert this constraint into the path integral. So and I'm also going to use the fact that if I write A times n minus sum over I, sigma I squared, that's equal to 0. So I'm going to add 0 upstairs. Doesn't change anything, because I'm just adding 0. So this is the partition function. We need to now, all we need to do, very simple, we just need to integrate over the spins. Then we've got the partition function. Okay, so the nice thing about this model is that you can just do now all the integrals over the spins. How do we do that? Okay, well, first of all, I'm going to use the following trick. So the first trick is that you guys see why that is? So I've just added the part where I equals j and subtracted it. And so I just have this squared. Okay? So so that's trick 1. And trick 2 is I'm going to use the following identity. So I'm just going to use the fact that, so now inside of there, I will have beta j over 2n. And I can write that as the integral from minus infinity to infinity Okay, so what have I done here? So I have this complicated thing where I have to sum over all. Yes? This one? Sorry, yes, that should be n. Yeah, that's 0. I've just added it for no reason. There's no reason why I added this thing. Okay, so I've written this this thing by introducing an integral over m, and you can just see by completing the square that this is a Gaussian integral, and if I do the integral over m, and there's a coefficient here. It's not going to be important. I have it here in my notes, but it's not important. But the important thing is that if you evaluate this on the saddle point of this integral, the saddle point of this integral over m is m equals, so m star, the saddle of this integral, is m equals 1 over n sum over I sigma I. So you see that we've introduced something that we're integrating over, and on the saddle, it's exactly the order parameter that we care about. So what does this buy us? So now what this buys us, if we plug all of this back into the integral, is that we have a bunch of decoupled Gaussian integrals over every sigma I. Every sigma I can do as a Gaussian integral. So I can remove this delta function using this identity, and all I get is this is A plus IZ over here. And now I just have a Gaussian integral over all the sigma i's. So linear term, but I know how to deal with linear terms, that's fine. So long as the real part of A plus IZ is positive, then I can do the Gaussian integrals without any issue. Are there any questions? Okay. So let me do the integral. It's okay if I erase this, right? Okay, so remember, all I have to do is integrate over n fields, but they're all decoupled. And I'm going to be left with a very simple integral expression once I do that. So remember, so we have the Gaussian integral. So for example, e to the minus 1/2 ax squared integral dx is equal to square root which way was it? A over 2 pi minus 1/2. So we just use that n times. And there's a coefficient here again. I don't care. But the nice thing is that now I'm left with, I started with n integrals, and now I only have 2 to do. And I have a big number out front over here in the exponential, this n. And so this integral, maybe I can do the integral over m. Again, it's Gaussian, so I could do it, but it's not very useful. It doesn't change much if I just evaluate this integral on the saddle point. So I just now have to evaluate this integral. At large n, the integral on the saddle point is very accurate. There's just this integral is very highly peaked around the saddle of this exponential. And then I'm left with an exact function of the temperature. But before I do that, let me just say that, let me first evaluate the saddle over z. The saddle over z gives me some z star, which is a function of a, and let's delete this. And I can plug this into the partition function, and then I'm left with an integral over m that I need to do. And that integral over m is now pretty complicated. So I can't really do the integral over m once I've evaluated over the z saddle. But I have a free energy that's a function of m now. It's just a function of m, and I can look at what it looks like. And it has a very nice form. So at high temperature, as a function of m, so this is the free energy expectation value as a function of m. This is m. At high temperatures, it just looks like this. So the system wants to be at zero magnetization at very high temperatures. This is what you expect. So the system at high temperatures, the free energy is minimized when there's zero magnetization, so the system is completely disordered. If you look at any one site, it might be pointing in some direction, but the average over all the sites, it will not be pointing in any direction. So the system doesn't have a spontaneous magnetization. But, so this is T much, much greater than T critical. But as I lower the temperature, something interesting happens. This solution at m equals 0 becomes unstable, and the system wants to spontaneously magnetize. So the system wants to live either here or here. So this is T below Tc. And the T critical for this system is the only thing that it could be. It's J, the coupling. So below T critical, the expectation value of m is not equal to 0. Actually, there's some issue that arises. How do you pick between these two solutions? You have to. There's a symmetry. M going to minus m. You can see in the Lagrangian, the original Lagrangian, that there's a sigma to minus sigma symmetry. Yes. T. So T is 1 over beta. The beta is the thing in the partition function over here. So it's the inverse temperature. Was there anything more to the question? No, T is something that you get to set yourself. It's just the external parameter. This is z of beta, z of T. So you just set the temperature that you want, and then you look at what the system does as a function of the temperature. Actually, this is z of beta and h. The two things that you are allowed to tune are the temperature. This is the inverse temperature. And this is the external bias. So really, here I'm plotting this at h equals 0. If h is not 0, then there's you get something like this. You break the symmetry. So this for h positive, it picks the positive m. And so what we mean by the expectation value of m so that's the limit as h goes to 0 plus of d by dh of log of z. And I think there should be 1 over n here. Take a derivative with respect to h in this partition function. You bring down this sum. You divide by n. Then you take h to 0. And that picks one of these vacua for you. Now, we see that, so this is the order parameter of the system, the magnetization. But say you're an experimentalist, right? Say you're an experimentalist and you're trying to understand where this transition happens. Of course, you don't have as much control over the system as we have here. Here we can do a bunch of integrals. We're very happy that we can do them without Mathematica. But in general, when you have a ferromagnet, you don't have super precise control over the system. And essentially what you're doing is you're trying to measure the magnetic field, but your measurement of the magnetic field is dependent on your apparatus. Maybe your apparatus doesn't have a very strong sensor for when the magnetic field actually starts, so it's very hard for you to distinguish where the transition temperature happens. Here we can define it, because in this model at this very particular J, we know that the magnetization all of a sudden goes from being 0 to non-zero. But if you're trying to measure it, maybe your measuring device is not good enough to distinguish where this thing actually starts. So you need something better to be able to experimentally verify where the transition temperature is, right? So how do we do that? Any guesses? It has to do with something that somebody brought up earlier. Any guess? All right, it starts with, no, let me take a lesson from Guy's book. And Guy, you get to answer. Nope. Ah. Oh, I had it right the first time. I had it right the first time. Yeah, so we want something that's discontinuous. Actually, one thing that's very nice to measure experimentally is something called the susceptibility. So let me define for you what a susceptibility is. So we have two parameters that we're allowed to tune. We're integrating over all the sigmas, but we fix the temperature and we fix the magnetic field, the external magnetic field that we're applying to our system. And one thing that experimentalists and theorists like to talk about is the susceptibility. So what's the susceptibility? So the susceptibility is actually the dependence of this order parameter m. And I'm sorry I'm being sloppy on when I use brackets and when I don't. But most of the time when there's an m, I mean m in brackets. The susceptibility is the response. So it's the response of m to a change in H. So we call the susceptibility chi. Usually what it is dm dh, specifically at h equals to 0. This is something that you have access to in your lab. You can look at how the magnetic susceptibility changes, or how the intrinsic magnetic field changes as you vary the temperature. And if you plot this, yeah, I'll just erase this backward. So if you plot this, it's a very typical thing that you'll see in a ferromagnetic system is that this thing looks like this. So it diverges at the critical temperature. And that's nice, because when you see something spike, then you have a good definition of something like a critical temperature. And actually, this gets me to your first exercise, homework exercise. So I want you to derive, for the spherical model, that so that's your homework. You have to show that this is true. So in this model, you see very clearly that this thing diverges, and it diverges with power -1. Very simple thing to fit. And it diverges with power -1 on both sides. Okay, so how much time do I have left? 20 minutes? 40 minutes, very good. Okay, so in general, what people like is very sharp features that let you define a transition point exactly. And these sharp features are things that people have become accustomed to. And over the course of the discussion on spin glasses, we're going to really see that this is the thing that's lacking in the definition of the spin glass transition. There are order parameters. There are things that we can define, but nothing that we can define that really diverges. There's no easy way to tell an experimenter, you know what? Just look for this thing. Look for this crazy feature that this thing is going to explode on you, and then you'll know where the transition temperature is. Okay. So no, it doesn't. Of course not. No, it doesn't. Experimental. The actual divergence is something that you can only get at infinite volume, but in real experiments, if you look at the plots, I mean, there is a very sharp peak. So you can open your favorite thermodynamics textbook or statistical mechanics textbook. They'll have pictures of stuff like this from real world experiments. It does diverge. Does the cutoff? I don't think so, no. No, not really. You just want to see that there's some kind of like sharp feature. Of course, you can't get real sharp features in any real-world system because all real-world systems have finite numbers of degrees of freedom. But you do see them get very sharp, especially if you take the volume to be pretty big. And what this is telling you is that at the critical temperature, the system is very susceptible to changes in magnetic field. If you turn on a tiny magnetic field, this thing will want to spontaneously magnetize. So it's very nice thing about this. It gives you something really sharp, and it's something that you can link to real physical systems, and it matches intuition. So it's a nice thing. And I want to tell you another thing about these susceptibilities. It's not going to really come up in this course very much, but it relates to a lot of things in theoretical physics. So I thought it was important to mention. So let's go back to this picture. So the mean field approximation that I mentioned is one that doesn't really accurately describe a real system. In general, physics is local, and the expectation value, the more realistic models have local interactions, nearest neighbor interactions or second nearest neighbor interactions. The all-to-all interaction that I described for you was one that's really nice for understanding the transition, but more general models like this one can be solved. And in fact, the spherical model with nearest neighbor interactions can be solved exactly too. It's not insanely difficult. If you're curious, I would suggest you try to solve it at home. It's not so bad. I think it was solved in the 1910s or something like that. So, I'm sure any of you could do it. Let's talk about the susceptibility for a theory with more local interactions. So the susceptibility, remember, the expectation value of M is the sum over all configurations e to the minus beta h of sigma. I've added an external magnetic field, sum over all the sigmas. And I'm going to just pick one site, sigma 0. If you have a translation invariant system, it doesn't matter if you have this, if you pick just one site at random. And then, of course, I have to divide by z. So what is the susceptibility? The susceptibility is dm dh at h equals to 0. And what that is I bring down this sum. So this is the sum over I of sigma I, sigma 0, minus the connected part that comes from taking the derivative over here. And if you look at this, well, in the continuum limit, I can write this as the integral of the connected correlator of my system. So now say I'm in d dimensions. So it's the integral over all space. You see this is sigma I becomes a position in the continuum limit. This is a 2-point function. So this is the integral over g of x. G is the 2-point function. And one nice thing is that for a large class of theories, if you just assume translation invariance, rotation invariance, then this G of x, it can only be so complicated. In fact, under minimal assumptions, this G of x will look like this. So it's usually parametrized using 2 numbers. So this thing we call the correlation length. It's okay, we'll keep it up. It's very important. Send your PDFs to anayelam@gmail.com. Don't forget. It's very important. Okay, so this just assumes that the physics is local and translation and rotation invariant. And most theories will have an expectation value for the 2-point function that looks like this. Doesn't require a microscopic model like the Ising model or the spherical model. Any model you choose, Wilson, Fisher, 5-4, whatever, your 2-point correlation function will take this form. And then if I just plug this in, then I get that this is proportional to the correlation length to the d minus 1 minus this parameter eta. So if I just stare at this plot and I connect the dots, this diverging susceptibility is just telling me that my correlation length is diverging. The domain walls are growing very large, things want to align, and all of a sudden I'm losing a scale in my system. So from very basic principles, we showed that the theory of phase transitions has a deep connection with this picture of losing the length scale, very large correlations. So, of course, we're not going to discuss this, but the theory at this transition point is very interesting. What is my eta? It's just a parameter. It's just a number. It doesn't. It specifies the model. So, eta will tell you, for example, it will be related to how this divergence happens. So you will be able to read off eta from this. Of course, in this model, there's no 2-point function because it's all to all, so it's not local. But if you solve the other one, you'll be able to read the eta. Okay. Now I'm going to quiz you. We want things that are sharp. Okay, so let's discuss something else that's sharp. One thing that you can define is something called the specific heat. Specific heat is very much like the susceptibility. Remember, I'm going to rewrite the definitions. dm, dh, h goes to 0. So the specific heat is like the analog of the susceptibility, but with the other knob. So we have the one knob that we have is the external magnetic field, but of course the other knob that we have is the temperature. So who remembers what the definition of the specific heat is? I'm going to wait. You guys have to answer. I think you said it. Of heat. What is heat? Okay. Somebody else. It's close. Maybe. It's simpler than that. It really is. It's not a very complicated object. Transfer of energy, almost. We're getting there. No? Come on, guys. You guys are very close, but it's a really simple definition. It is the derivative with respect to temperature of, no, the energy. It's just how much the energy of the system changes as you change the temperature. That's what is the specific heat. All right, so part 2 of the quiz. So how do I compute this expectation value of the energy? It is not. Very good, very good. With a minus sign. So this is d by dt of d by d beta of the minus log of z. And log of z we actually often call the minus of the free energy, so with the beta in front. So this is d by dt of d by d beta of beta f. So for those of you who don't remember this, so here is our partition function. I was taught back in the day when I was very young, before the advent of ChatGPT and all that, that you have to know how to rederive everything just in case you accidentally end up on a desert island. Because if you can't, if you don't have your textbooks, then what are you going to do to spend your time when you're on the desert island? So of course I followed that growing up. So your partition function, remember, is the sum over all configurations, e to the minus beta h. And if I take the log of it, and the log of this, and then if I, of course, take d by d beta of that, I get, with a minus, I get the expectation value of h. That's why. It's very simple. And the specific heat is then the derivative of that with respect to temperature. So if you study, for example, the Ising model, then one nice thing is that in the Ising model, the critical temperature for the specific heat is the same as the specific, the critical temperature for the magnetization or the magnetic susceptibility. So if you look at both the magnetic susceptibility and the specific heat as a function of temperature, you get that they both diverge at this critical temperature in the Ising model. Now, in this model is a little bit bizarre. This model with all-to-all interactions, the specific heat as a function of temperature looks like this. So it's 1/2 below T critical and 0 above T critical. So yeah, homework 2 is to derive this for the spherical model. Okay. So last part of the quiz. How do I compute the entropy of my system, the thermodynamic entropy? Does anybody remember? One minus beta d beta log z. That might be right. I actually, I would have to check. I didn't write it that way. Well, we're on a desert island right now. I hope you guys put your laptops away, otherwise you'd be cheating. Let's figure it out. So, let's remember, how do I define my free energy? Thermodynamically. Yeah, there's the energy part. Minus. Yeah. Very good. Huh? Okay. And this is the internal energy, right? So let's rewrite this. So the internal energy is d beta of beta f, right? So let's use the chain rule. So d beta by the chain rule is minus t squared d by dt. This is dt d beta, and beta is, t is 1 over beta, so dt d beta is minus 1 over beta squared, and then f over t, right? And let's just turn the crank. So let's take a derivative of the 1 over t. We get minus t squared times minus 1 over t squared f, and then plus 1 over t d by dt of f. So I get that this is equal to f minus t dt of f, and that's equal to E. So let me rearrange. I get that f is equal to E plus t dt of f. So does anybody know what the entropy is? Nope. It's the desert island. That's how we got to do it. That's all we're doing. Okay, so exercise 3 is to compute the entropy of this system and observe something weird. Okay. So in general, we really want things that diverge. That's how we define critical temperatures. That's how we define our theory of phase transitions, at least static phase transitions, thermodynamic phase transitions. Here's an example where we can compute a bunch of stuff, gain intuition, and see what happens as we tune the temperature, as we tune the electric field, or the magnetic field. And here in the theoretical model, we really do have these sharp features of the transition. You can compute from first principles everything that you want to know, and you see exactly the telltale signs of a phase transition. But what happens in glasses? So now I'm going to end with a brief discussion about what happens in the experiment of glasses. So remember, this is going to be the phenomenology of glass formers. So remember, the first thing that I said was that many of the things that form a glass only form the glass when you cool them slowly. So have you guys ever watched a video of somebody blowing glass? Yeah? So what do they do in those videos? They blow and then what? They put it in water. Yeah, so there's a very hot system. They put all of their silica in the hot kiln. Then they start like pulling on it in all directions. And then when they like what it looks like, because this thing is a liquid, right? It's flowing. They're able to pull it and all that. They shove it in water. And then it gets stuck, right? And that's an important part, because if they didn't throw it in water, then this thing would remain a liquid and then it would lose all of its structure. So part of the annoying part of forming a glass is that the physics depends on cooling speed. And that's something that's really hard to model. How do you do that? How do you build that into the model? That's one tough part. Number one is that we had some very harebrained, very bare bones system. We put a bunch of spins on a lattice. We say they're coupled in some way, and then what we did was we cooled it down, and all of a sudden everything wants to be ordered. That's fine, but apparently, if I took my system of spins on a lattice that all want to be ordered together as I cool the temperature, I heat it up, and then I cool it really fast, all of a sudden that physics is completely wrong. What the hell? What went wrong in my little toy model that I described over there? So that's step one. Physics depends on cooling speed. And step two is that nothing diverges. If you could find the quantity that diverged at the glass transition temperature, then you would probably win a Nobel Prize. So there's no experimental evidence that anything diverges, no order parameter that anybody can come up with that actually signals this transition. Nothing diverges at the transition point. So what do experimenters see when they're trying to study glasses? So one thing that they see is something I mentioned earlier. So we're going to define this as T glass over T. So we're plotting it in terms of beta, not in terms of T, for a bunch of different glass formers. And this is the log of the shear viscosity. And what people see is that for various amounts of glass formers, it's very, very interesting, and this plot doesn't show how quickly you cool, but it's an important feature in how the system forms a glass, is how quickly you cool it. But suppose that I cool it fast enough so that it evades forming a lattice or a crystal, and I decide to show that, or I decide to just plot this viscosity as I approach this glass transition temperature, and you get a bunch of different behaviors. So first of all, this is a finite point. And they're all going to the same point. Then you have some plots that look like this, some that look like this, some that look like this. Okay, so do you guys know how to read a log linear plot? Do you know what this is showing? So what about this straight line? What does this mean for the viscosity as a function of temperature? Sorry, I can't hear you. Power law. Not quite. Yeah, this is exponential. So that means that the shear viscosity is E to the Tg over T. Linear. And what these guys are doing is exponential to a power. The other guys. And these guys are exponential to the exponential of a power. And they're all forming a glass. And this point is this point, 1,010, what is it? I forget the number. It's some large power of poise. I didn't write it down in my notes, so I'm not going to say what the number is. But this just tells you that the viscosity slows down enough that the experimenters got too lazy to wait. And they defined the transition temperature to be the point where they agreed to be too lazy for all the different materials. But this is bizarre, right? Like a glass former, the approach has nothing to do with how they call it a glass. Just exponential approach or super exponential approach. They call that a glass former nonetheless. So already we see that we don't really have any good experimental design for distinguishing what the physics is of this transition. And of course this is recorded, and I'm not an expert, so maybe somebody's going to email me very angrily. But the fact remains that there's no discontinuity here. This is going to a finite point.
Tarek, sorry, one question. Can you repeat what are the different curves or different materials?
Different materials. So this is material 1. And yeah, it's this is taken from a classic review. I can give the reference to anybody who asks. But yeah, all these are different materials that they did the test on for forming the glass. Like what the viscosity, how the viscosity grows as you lower the temperature.
And for a single material, if I cool it faster and faster, do I see that?
Do you see a change?
Yes.
In the behavior? I don't think in these curves you would see anything, but I think that there are, yes. So there are, very good. That's something that I wanted to mention next. In this experiment you wouldn't see, but there is something time dependent that depends on stuff like cooling rate that arises in the theory of glasses. But I just want to emphasize how confusing this is, like from the perspective of a theorist, right? We're supposed to, all of us agree that glass is a different phase of matter, right? Like it's not the same as a liquid, but how do we characterize it, and what is the universal feature of this transition? We have no idea. So that brings us to the next point, which is that so these things, yes. That's the temperature at which these guys reach 10 to the some power that's like 13 or something poise. You're asking me? This is our best definition. So if you're motivated to solve this problem, I invite you to do it, because many people are confused and we need new ideas, I think. I'm not an expert. Sorry, YouTube. I don't want to overstep my boundaries, because I'm sure somebody's going to put a comment like, this guy doesn't know what he's talking about. So yeah, indeed, very confusing state of affairs. The next thing that I want to mention is that there is something that is inherently like ever present in glass forming materials, and that's something called aging. So aging is the phenomenon where, say that you are beyond tea glass, so you're definitely in the glass phase, whatever that means, and you apply a deformation or a kick to the system, and you want to see how the kick relaxes. So what you can do is, for example, if it's some kind of like spin magnet, which is like all the magnetic moments are frozen, but it's like frozen in a glass state, then what you can do is you can apply a magnetic field onto the system, try to bias the spins in some way, and then turn it off. Right? So let's say that we have this external magnetic field H, and the profile looks like this. Turn it on for some time, TP, and then I turn it off. And the strangest thing is that the relaxation, so M as a function of T, follows some behavior that goes like this, and it's something like minus log of T over TP. So there's no characteristic scale to the system itself, and it picks up the scale of the perturbation. And yeah, good luck modeling that. There are some toy models of it, but having a deeper understanding of this behavior would be great, I think. So what we're finding, or at least what I'm giving you a prelude to, is that glass formers are very different from this nice sharp picture that we have of phase transitions where things diverge and correlation functions are local. So for example, this idea of susceptibility that I showed you earlier, the phase transition really has to do with how the correlation length is growing as you approach the transition temperature. But the correlations, if you perturb the system, nevertheless look local and depend on characteristic scales of the system, which, if you're powerful enough, you can compute. But I don't know. I think that the leading behavior is this logarithm without a power in front. But there could be corrections. But I think they depend weakly on time, if any. Because, you know, like any power washes out logs. So I think this logarithm is very, I guess, robust experimentally. So what people claim is that this logarithm and this dependence on just the time of the kick has to do with the fact that this thing is multi-timescale physics. or sorry, multi-scale physics. You have a bunch of competing scales that are activated at the same time. Your system is kind of stuck. And when you sum over all those scales, you get something that doesn't depend on any of the scales anymore, and you're left with something that depends on the time of your perturbation. But how do you get a model with multi-time scales or multi-scales? Like, it's difficult from just trying to write down some UV model that you can just study to death and get the nice physics of. So, yeah, yeah, in the last few seconds, I want to emphasize that what we're going to study over the next few days is that what we're lacking is sharp. So the experiments haven't really given us. They haven't really given us anything concrete to hold on to. For example, the theory of ferromagnetism due to Pierre Curie is from the late 1800s, and it was very quick from then to the study of the Ising model and the understanding of phase transitions, where we were supposed to go. But it was first led by experiment. There was some experimental result that told us, oh, at this transition temperature, if I measure the magnetic susceptibility, or if I measure the thermodynamic response to changing the temperature, all of a sudden I see something diverging. So probably this is how we define this transition temperature. It was in fact his PhD thesis, I think. And we're not in such a strong state because the experiments aren't giving us something nearly as sharp. They're a lot harder to deal with from a theoretical picture. So our goal over the next few days is to try to take that in and maybe see something that maybe experimentally isn't so sharp, but nevertheless may have some experimental implications. And we'll discuss what those are in the next few days.
Questions?
How would you see this aging thing in physical, let's say, a glass blowing model, or the glass blowing picture? Is there a way to see the aging part?
I mean, there's some understanding of it. The only thing I've seen is this discussion about how summing over multiple scales washes out the scales, so you're left with something that only depends on the perturbation time. But building a model that has multiple scales that is also solvable, very difficult.
No, I meant like this is in the context of a spin glass, right? In the context of a
no,
real.
No, what I'm talking about with this aging is in real glasses.
Oh, okay.
Also spin glasses have it, but real glasses. Oh, there are things called electron glasses, which you can build, and those are kind of like spin glasses. They show this. But that is to say, like, I don't really want to make a distinction between a spin glass and a regular glass, because I think that might be contentious. I don't know. Sorry, YouTube again. But some people might say, they're the same, and some other people will say, no, it's very different. Until we have a sharp way to distinguish between the two, I'm not going to make any claims myself. So.
Could it be that the non-divergent behavior of the glasses is related to the fact that you're changing the boundary conditions in an adiabatic way, such that the system has time to react in a nice, in order fashion, and when you perturb a system in a very fast way, you introduce a scale that might this, require that you change what is the
Yeah, of
description of
course.
the system.
Of course. I mean, if you think about it from the perspective of the renormalization group, what this is saying is, our basic picture is that, the phase transition is that there's some kind of relevant operator that becomes important, and all of a sudden the physics changes as you flow to the IR. And here what this is telling us is that there are other relevant operators that you can turn on in your system that become relevant when you cool the system super fast. But what those operators are, I don't know how to characterize them.
Thank you.
Hi, thank you for the class. I was wondering, you showed us this viscosity shear graph, okay? But I was thinking maybe there are another quantities that you can analyze for infer about the phase transition, for example. Not only the shear, and there is any discontinuity in something, no? Okay, so how do you know there's a phase transition?
Good question.
Okay.
No, I'm serious. If you had an experiment that has a discontinuity, then people would rejoice. But there's beyond the fact that we think the glass is a different phase. We don't have a way to really sharply define it.
I have a simple question. For comparison with that plot, suppose I cool slowly. I would say that if you turn on a field, then your smoothly ordered phase will have a magnetization that grows in time, and then does it get stuck, or like it doesn't age at all, right? Or
In a real magnet.
Yeah, in a real magnet.
Not a glass form.
Well, in your model, in the simple
this model that I discussed, just to like set everything up where there's no spin glass phase. So like, this is just a model of a ferromagnet. That model would not age.
that model would age. Okay, okay.
Not
And
age.
in a real magnet, of course, you will age at some time.
If you age, I think that you age like in the early time, which we don't think of as the universal part, and then it'll decay. It'll decay at some characteristic scale of the system.
Very good, very good. But in a very, very stupid model, the
So for example,
ferromagnetic doesn't age.
In the Ising model, there's a light particle. If you move away from the transition, there's some like spin wave. That's a light particle. It has a mass, and things will decay with the mass of that particle. Okay. And that's it. The early time stuff that's going to be polluted, you have no idea. But at late times, that's the only scale that matters. So.
Okay, thanks.
One stupid question, maybe. So here you're thinking of this glass phase transition by cooling the system really fast. Can you also have this kind of phase transitions if you change, for example, the volume really fast? Instead of...
Maybe. That's hard to do experimentally. I don't know if anybody's done that. How do you change the volume quickly in an experiment?
With an inflaton.
You're asking if, well, Guy will have to tell us if the, I had this, okay, maybe, yeah, YouTube, sorry, YouTube. There's this, what if the seeds of all of the inhomogeneities is just that you supercooled and you're in a glass phase, and the evolution is something like that, Yeah, some frustrated system that, like generates its own, it starts in some ordered phase and then it inflates and then it generates its own disorder, and then what we're seeing is that you maybe need less of a theory of initial conditions if you generate your own initial conditions, if you know what I mean. There are some glasses that can do something like that. Well, we'll discuss one. I don't want to like give it all away, but we're going to discuss a model. So we're going to try to solve it. I'm going to tell you how to do it. So just wait. It's going to be fun. More equations on the blackboard.
Let's thank Tarek again. And we meet after lunch.